Ladies and gentlemen, good morning. Thank you very much for the invitation. It was put to us, the question is addressing the question, engineering schools adapting to change, how much, how fast, and in what way? And I thought, actually as I walked into the building, it says change the world. Well, and I'll try and add a bit to that. But perhaps the way to start this is by considering what sort of changes is it that we actually want to or expected to adapt to, and indeed, how do we interpret the term adapt in the first place? And are we seeking to react or respond to some change out there, or is it that we actually should be doing is to aim to proactively bring about the change in the first instance? Now, these are, of course, not mutually exclusive, but there is a subtle difference. And then the question arises, so what are the changes that we need to want to adapt to? Are these technological changes? Are there scientific changes? I mean, we recently had the discovery of gravity waves. Societal change, climate change, political change, all of the above. And then how do we, as engineering schools, deal with that? Many ways to explore. One way, I think, to explore is to pose the question, which is a sort of obvious question. So what are engineering schools for in the first place? Now, I'm sure everybody in this room will have a view, but let me sort of approach it from three very obvious angles. The first one is, I will all agree, I think, that the engineering schools are about educating engineers. But I would like to add for the future, and this is the angle I'd like to take. And it's not only what we teach, it's also how we teach them. But what do we teach them? And this is a great generalization. So what do we teach them? Well, we start off by teaching them a bit of science, and by science I would take natural science. I spoke to our Faculty of Science the other day, what they consider to be applied science. This is tongue-in-cheek. Maths, physics, chemistry, I consider to be basic science, but this is a whole philosophy in own right. We teach this bit of science, then we teach a lot of engineering, and that sort of evolves to technology and how to apply these. And then, of course, we also teach what many of us would refer to the soft skills. And this has changed as well. A long time ago, when we thought IT was a soft skill, what we taught them in IT was how to use a word processor, spreadsheet, all of that is taken as read and has moved on. So IT sort of soft skills has moved on to cybersecurity, focus on knowledge management, big data, all of that has changed. A lot of engineering curricula these days would inevitably include a course on ethics and environmental responsibility and so on. This is slightly different from how the way we teach have changed. Nowadays it's almost taken as read and to a large extent accepted by students that technology-enhanced platforms will be there. And these include simulations, e-learning, e-books, online collaboration, MOOCs, 3D printing, remote labs, virtual reality, all of those things. The second bit of what engineering schools are for, I would put, is research. And the angle that I like to take is creating new knowledge for the future. And then the third one that I would like to put on the table, what engineering schools are for, are engagements. How do we engage, again, for the future? Because as engineers and engineering schools, we constantly engage with various communities. And this might be society in general, it might be our professional environment, and often as engineering schools, we have to engage with the rest of the university in some way or another. And again, we need to consider whether we do this in a reactive mode, or alternatively, whether our aim, and in fact our responsibility, is to influence and shape the future. And that's the whole thrust I want to take. Now, there's an interesting example in the engagement bit of shaping the future. So lawmakers and governments across the world recognize to a more or lesser degree the requirement for technological and scientific advice as they go about their business. And many countries have structures in place to do that, including the UK. So as an example, to illustrate the sort of problems that can occur when lawmakers ignore scientific facts or technological facts, they ignore them or they discard them when making policy and legislation. Let me give you an interesting example. So the mathematical constant pi, we all know, is the circumference of a circle divided by its diameter. And pi is well known, and the value is 3.141592653, and it's an infinite series. This is pi, and we all know it. It's a universal constant with infinite number of digits. But it turns out that in 1897, a bill was introduced in the House of Representatives in the great state of Indiana in the US, and this bill suggested 3 different numbers for the value of the constant of pi. And the reasoning was, 3.1416 is very difficult to do. Why don't we just make a law and pi will be equal to 3.2, much easier to deal with. So they introduced this bill, and it was referred to the Committee of Education, which passed it no problem, went on to the House of Representatives, voted unanimously 67-0. So from now on, in Indiana, pi will be equal to 3.2. They then sent this bill to the state Senate, which referred it to one of its committees, passed the first reading, and at that point, a professor from the University of Purdue happens to walk by and hears what's going on, steps into the Senate and saves the day. So the bill then died a quiet death, and to this day, pi is equal to 3.141 whatever in Indiana. The local newspaper reported that although the bill was not acted on favorably, no one who spoke against it intimated there was anything wrong with the theories it advanced, and all the senators who spoke about this bill admitted they were totally ignorant of the merits of what they were considering. So I think there's a role for us to say proactively engage with the future. Now they say there are 3 types of people in the world. There are people who make things happen, there are those who watch what happened, and then the third is those that wondered what happened. Now if we take this as a law of nature, in a tongue-in-cheek way, our role is probably to contribute, to proactively contribute towards shaping and creating the future, rather than just accepting a world that others have given us. And as engineering schools, we must also instill, I would think, this ethos into our students. Now, in order to do this, it is useful to explore a couple of characteristics of the future. And again, everybody will have a view. So let me put to you 2 or 3 characteristics that I think are relevant in this discussion. The first one is that the future will happen. And most of us will be there, at least for a while. I can easily say out there, great philosopher, I've thought about this and I really don't believe in gravity anymore. Well, gravity really doesn't care whether I believe in it. It's going to happen. Same with future. Now, the next point is it probably won't happen by itself. People out there are going to do stuff that will make it happen. Right. So, and I've already sort of hinted that I think as engineers, and particularly as engineering schools, we need to educate people with a mindset that they have to proactively create the future. And the third characteristic, I think, of the future that it may be relevant here is that we don't know exactly what it's going to be. In fact, in some cases, we have no idea what it's going to be. But what we do know, it will be different from what it is now. Right? There will be change. Now, good morning. There will be change. Now, hopefully, the change that come about, we can refer to as progress, i.e. change for the better. But it will be different from what it is now. Now, whether we call this change that is going to happen between now and the future progress, or as we'd like to think of it, continuous improvement, the fundamental concept of change then becomes central to our discussion. And it is useful for us to consider. So what are the elements of change that we need to think about? What I'd like to submit is not only, thinking about the question of change itself, what do we do about it is important. So we need to understand and think about how we can influence change, and that brings onto the agenda the notion of change management. Right? So change management, I think, becomes a very important one. There's a professor at Harvard Business School, John Cotter, and he actually uses the term change leadership rather than just change management. And I think that's a much more inspiring way, is to say what we should be thinking about is how do we stimulate change leadership. All right, so as engineers, we deal with change on a daily basis as we go about our engineering business. As a matter of course, we design and build new things to replace older ones. And we know the day will come when somebody else will decide something that will replace what we've built, and ours will be, taken out of the way, hopefully recycled in an eco-friendly manner. But we know that time will come as well. Now, often what we do is we don't refer to the change we deal with on a daily basis by calling it change. We have other technical terms for describing how things change with time. For example, and this of course we call the dynamics. So distance covered as a function of time we like to call speed, and as the speed changes as a function of time we like to call it acceleration, and the number of electrons flowing per second we call current, and so on. And this is all change, we just don't necessarily think about it that way. But we deal with change on a daily basis, whether it's in these technical terms or whether it's designing new things. It's fundamental to what we do, and engineers generally no difficulty with the concept of dealing with change. However, if we stand back a bit and to say what our role or maybe our responsibility is we need to ourselves and as engineering schools instill in our students the ethos of part of what they need to do is change and shape the world to create a better future. Maybe the other sort of changes we need to think about as well as we go about our business as engineering schools. And the one that I'd like to focus on is the dynamics of technological change. How technologies themselves change with time, and how do we, and if we believe this is important, how do we integrate this into our curricula? Not only because it might be of historical interest to some, but I think, and I'd like to make a case, that the dynamics of technological change is fundamental to our ability to shape the technological future, particularly through a more structured approach. And the vehicle we take this forward is the management of technological innovation. Many economists out there will tell us that technological change is one of the most important drivers for economic growth and societal changes and so on. The question then is, how do we integrate this notion of change management or change leadership, particularly technological change leadership, into the curricula, into our research agenda, and particularly also in the way we engage and the way we sort of inspire our students to engage. They want to become the professors of Purdue who walk into the Senate and stop being people doing silly things like, making a law to change pi. Now, I remember vividly an incident that happened in the second year of my study. So I studied was a 4-year degree in electronics engineering. So at the end of the second year, which is a great moment because second-year students, as we all know everything. So end of the second year as an undergraduate student. This was the year 1977. Now, some might recall and some might not, that was the time. So what happened that was the time when the 8080 Intel microprocessor was just the biggest thing around. We were just getting rid of slide rules and sort of using calculators. In fact, programmable calculators were just coming onto the market. And there was one HP, I can't remember, a little thing that slided through and you could download it. You can see some people smiling on that. That was long before the wide use of personal computers, not even to speak about the internet. But from a technology viewpoint, that was about the time where transistors were sort of established and studying electronic valves were dropped from the curriculum. And the next big thing we were sort of studying, they were coming along with how do you design integrated circuits. So that was the time we were talking about. So we sit in a room like this, and then big professor walks in and he says, today I have good news and bad news. He says the bad news is that the technology that you students, that we're teaching you, that you're studying, the half-life of that technology, electronics engineering at the time, is barely 3 years and decreasing. Now, and of course he was referring to some sort of a variation of Moore's law, although that wasn't the way he put it to us. Now, this is not what you want to hear when you're halfway through a 4-year engineering degree and you realize that half of what you're going to be studying is obsolete before you even graduate. Or that, you know, that's the sort of way many of us interpret it. And as you can imagine, silence in the room. And then he continues. And he says, however, the good news is that the sort of education we want to give you at that particular university, you the students, the sort of education will equip you, the students, to become the people that are going to actually create all these new, exciting new technologies and technological solutions that will make the old ones that you're studying now obsolete. So with a few words, and those few good news and bad few words, he opened our eyes to a completely different view of the world and the future, and also the concept of the future, and what our roles as new, bright-eyed engineering students would be in this new world, into the future. And what he was trying to tell us, that what we were learning were the principles and how to apply them to create something useful. And at some point, the principles will become obsolete in the sense that the principle can become overtaken by other principles that were more relevant to new engineering technologies. I mean, the principles that you use to design valves are very different from the ones you use to design transistors. And what we should be able to do is learn not only the principles, but actually how do you develop the new principles as the new technologies come along. It was a very transformational moment for that class of students. At the same time, once you start thinking about it, you also come to the realization that what he was also saying was, in life and in engineering, real engineering, the answers are not in the back of the book. That's a luxury reserved for first-year tutorials, I think. But we understood that the value of a principle lies in a number of things that it explains, and that shaping the future often involves framing the right questions in the first place. Never mind the answers in the back of the book. Later in life, I learned another sort of lesson from what he was saying. And it was this, that another very important characteristic of applying the principles of dynamics of technological change is the following. Then whenever there's a change in the technological regime, for example, an industry will be built upon building equipment that uses electronic valves. Somebody invents transistors. So from there on, equipment uses transistors, and then so on. So when the technological regime in an industry changes, it usually has a very profound effect on the entire structure of the underlying industry. Because as the technology changes and a new one becomes dominant, the ecology changes with regard to market leaders. So if the dominant technology is valves, you will find that the industry leaders, the companies, are companies A, B, and C, usually. When the technology regime changes, the leadership changes. Then the new leaders in the new industry, in the same industry, become companies D, E, and F. And then they switch to integrated circuits, and after a while, the leading companies become X, Y, and Z. Very difficult for companies to switch and maintain their leadership positions as technology regime changes. Now, if you understand the dynamics of technological change, it's not too difficult to figure out why that happens. And it's a phenomenon that happens very often, to such an extent we can almost call it a law of some sort. Now, I think in order to educate our engineers, we need to educate them as change leaders in general, and technological change leaders in particular. And then I would like to submit that they must, in order to do so, they must understand the science of the dynamics of technological change, because it is such an important driver for many of the other changes they will need to deal with as they go through life. Why do I say science of the dynamics of technological change? Well, it turns out that there are many laws that govern how this works. Some of them are laws of nature in some way or another. Some of them are laws that govern behavior of people. But in there, there's a structure and there's a science. And it is something you can study, it's something you can learn, and it's something you can apply. And if you don't do it, I think you do it at your own peril to neglect that. So part of my submission is that the dynamics of technological change is fundamental to what engineering schools should be about, although we don't often think about it in those terms. And if we agree that that is the case, then we should also be, the question is, well, we should be teaching in not only the engineering or technology of today or tomorrow, but the technologies of the future and how we interpret what the future really means. The question then becomes, well, if all of this is, makes sense, then how do we integrate this concept into our curricula, in our engineering curricula? Which, of course, is something completely different from how do we integrate new technologies in the way we teach. Now, let me propose one approach in which we can think about this. And it's based upon the theory, and I think it's more a suspicion than a theory, if you will, that many, and certainly not all engineering curricula, exhibit characteristics, what I sometimes think we should call the perils of the linear curriculum. And what this is about is the implicit assumption or presumption about the relationship between science, natural sciences, and engineering and technologies that follow. I know this is a very contentious subject, but let's just go there anyway. So let's take a hypothetical 4-year engineering degree. I know in the UK many engineering degrees are 3 years, other countries say 4 years. So let's take a hypothetical 4-year engineering degree. And how will that go? Well, the first year, probably you will do a lot of basic sciences, a lot of mathematics, chemistry, physics, and for good measure, you'll have some sort of a soft skill on the side or introduction to engineering or something. But basically, it's a lot of maths and chemistry and physics, which you need to know in order to do the rest. You move on to the second year, and then what you'll find, you'll have more applied sciences and sort of start with basic engineering. So in my line, you start doing electric circuits and so on. The third year is more applied engineering, with perhaps the odd advanced course in science. Some engineers might need more maths or advanced physics or advanced chemistry, but basically more engineering. And then you get in the fourth year, and it's very heavily applied engineering, usually with some very large capstone project that takes all of it together with a very comprehensive design in it. So that might be the structure of many 4-year, others, but there might be some. And then if you look at it, what you might find is the anatomy of this course is there are lines built in there. And the line typically starts with some sort of a basic science and progresses from there on to an advanced engineering bit at the end. One line, as an example, might be is you start with mathematics and physics in the first year, and then in the second year you start doing a bit of material science built on the physics, and you do a bit of electric circuits, and that then equips you to do integrated circuits as you move into your final year. So it starts with basic science, bit of basic engineering, and so on. Another line might be, well, you start with mathematics, and then the second year they'll teach you Fourier transforms and Fourier analysis and so on, and that then eventually leads to the engineering study of signal processing. So then, and in your area you might have others, but that's basically the sort of suspicion I have. Now, if this linear paradigm, if it's true, and if this linear model we use, if you will, the dilemma that you need to resolve is what happens if there's some very important engineering concepts that you need to learn, and typically in the later years, but there's no basic science to start off the line. Where do you plug that into this linear paradigm? Because there's no basic science, and you need to get this into the... So what's the dilemma? And very often people will just squash it in somewhere. For example, manufacturing. Still trying to figure out what is the basic science, natural science, that starts off the line that leads you to manufacturing. Now maybe there's an answer, but for my story now there's not. Okay, so manufacturing. It doesn't fit into the natural flow of this linear paradigm, of which I have a suspicion is inherent in many engineering degrees. Now it may just be that the dynamics of technological change as a subject can be that science that's, if we integrated it starting from the first year, that starts off and solves a lot of these issues. That might be the science, because if we say the dynamics of technological change is that science, that then develops into the management, or leadership if you will, let's call it management of the process of technological innovation. And that might be the key to this whole dilemma, because again, the management of technological innovation is not some mystical thing out there. It's something you can study, you can learn, you can understand. And again, I think if you don't, then you do it at your own peril. Now, there are many definitions for innovation out there. Let me take one very simple one to make the point. And it's basically that innovation, successful innovation, is two components. There's an invention component, and there's another component. Now, let me call the other component for the moment the adaptation component. And by adaptation, I don't mean adapting the technology. I mean users actually adapting this invention to use it. And that's it's often referred to as diffusion of the technology and so on. Now, the invention component, this is where we create the new knowledge, usually some sort of engineering or technology knowledge, but inventions create new knowledge. And it's based on discoveries. It's based on creativity. This is where you use your own new original ideas. A lot of it has to do with using other ideas that are out there, read somebody else's paper, adopting, changing, beg, borrow, steal, royalties, whatever, and you create a new invention. But what we need to do is to add something else to the invention so that that invention actually is being used. And sometimes they say this is called the adaptation component, the diffusion component, or whatever, that turns the invention into an innovation. And it's much more than just marketing. The role the market plays in all of this is very important. But this other component is much more than just marketing. So whereas inventions create new knowledge, innovations actually create new wealth. And that is the big difference. There are many companies out there that are not necessarily successful companies. And their strategy is not necessarily to be the best first-to-market inventors. There are many successful companies that say they will be fast followers, and they focus on the second component of the innovation bit to become very successful innovators, often using other people's inventions in some way or another. But they build their success by focusing on the other component. Now, similarly, I suspect, or it's a theory, that underlying many of our focus in some engineering schools, either by design or default, good morning, we have the same thing, so that the outcome that we have, and again, either design or default, is we deliver fantastic inventors. So inventing is one of the aspects, one of producing engineering graduates who are great inventors in a broad sense. They know how to create new knowledge. I would like to submit that is not enough. Because if the people we produce as our engineering graduates are to shape the future, we must focus on engineering schools, on educating and producing innovators, of which invention is a necessary but not a sufficient condition, particularly technological innovation. So if this is the line, what is it that we will teach them, keeping in mind this linear paradigm? Well, we can start off by teaching them the dynamics of how technologies change. And it's very much about how F-curves fit in and emerging and, Then the difference between the radical and incremental innovations. Because the radical innovations are where the new breakthroughs are created, from valves to transistors, from propellers to jet engines and so on. We will also show them the importance of incremental innovations, which are by far the most prevalent type of innovation out there. And by discussing incremental innovations, you naturally introduce the notion of continuous improvement and quality management into the curriculum. Both radical and incremental innovations are important, but each has its place depending on the maturity of the technology. And each one of those has a different strategy in which you manage it. We teach them the difference between an invention and a product, because it is not always the best technological solution that gains market dominance. There are other forces at play. The keyboards we are typing on today are known as QWERTY keyboards, the way the keys are arranged. While you can, and some people have, come up with a better combination of keys that will allow you to type faster. Now, if you go today and you try to introduce that keyboard to the market, it won't work. Nobody will buy it. Why? QWERTY keyboard has become the dominant design. If you want to break into this market, you need to come with something completely different, like voice-enabled, or reading brainwaves to get it into. Another keyboard just won't do it. It's the dominant design out there. Now, this theory of dominant design actually is very closely based on the interlinking between product innovation and process innovation. And that's how we bring the notion of process innovation into play. And once we introduce it into process innovation, it's not a big jump from process innovation to manufacturing. And that's how manufacturing gets into the line. So the key to all of this is technological understanding, the dynamics of technological change as a way of educating our engineers. Before I stop, I want a few words about, quick few words about the soft skills, because they are equally important. So the notion of change leadership, the ability to manage change, also resonates with the soft skills, which are very important. Often has to do with the so-called work readiness of our graduates, keeping in mind that we are not training people for a first job. We must educate them for a lifetime's career. They need to create the future that doesn't even exist today. So the question is, what are the soft skills you put in there? So everybody has a view on soft skills. Now, there's a paper that was interesting I found, and it came from Australia, Hartman and Jaron, 2013, reference out there. And the question they posed was the following: what are the most prominent competencies companies are seeking when they use leadership in job descriptions for entry-level full-time engineering positions? It's a big study of all the ads. And not surprisingly, they came up with strong communication, teamwork, interpersonal skills, and in the case of construction companies, interesting enough, conflict resolution was another skill. But that's another story. I would submit, sort of in conclusion, that the soft skill that we're after is change management skills, in particular, change leadership skills. And maybe that's even a hard skill, I would think. So let me say the approach that I found stimulating is there was an article by a chap called Roger Dickhout published in McKinsey Quarterly in 1997, and it was title says it all. All I ever needed to know about change management, I learned at engineering school. And it has a bit of a go at says mechanical engineers about making things go round and round, the dynamics, civil engineers about making them not fall down. I think there's still a dynamic in there. Time constant might be different. And then it quotes the laws of engineering that you need to apply to change management. So it's the laws of constituent balance. Why does a current flow? Well, there's a potential difference. In chemical engineering, if there are pressure differences, it will change. There's a law in there. Nature abhors a vacuum. Law of leverage. Archimedes, give me a lever, I'll move the world. 80-20 principle. He says 60% is often enough, or 40% just you don't even have to bother to start. Law of momentum, liberating the energy to bring about the change. Feedback and adjustment, how do you feedback? The important thing is the law of leadership, stressing leadership is the catalyst for change. Now it's in chemistry, small amounts of a catalyst intensifies, accelerates the reaction. Often you have everything except the leadership, nothing happens. So, summing up, we started off with engineering schools adapting to change, how much, how fast, what daily basis of engineering that we deal with dynamics, how things change with time. It's not new to us, it's what we do. I would like to suggest that we take forward a broader approach to change. Engineering schools will embrace the notion of change leadership and management of change, reflected in our curricula, in our research, and in our engagement, and suggest we integrate the principles of the dynamics of technological change as the science that underpins managing technological innovation in our curricula as a key towards empowering our students to become change leaders who have a vision